In the last episode, we discussed the Arrhenius acid-base theory. This time, we look at acid-base with another theory that is called Brønsted-Lowry theory. In the Brønsted-Lowry theory, an acid is defined as a substance that can donate a proton to some other substance. All the Brønsted-Lowry acids are proton donors. The base in Brønsted-Lowry theory is defined as a substance that can accept a proton from other substance. They are proton acceptors. Well, let's look at an example. If we dissolve hydrochloric acid, HCl, in water, what will happen is that a proton from HCl, a proton, remember, is an H+, will be transferred from HCl to water. Water, after getting an H+ proton, now it has 3 hydrogen, before it has 2. After getting an H+, it has 3 protons now, 3 hydrogens now, and a positive charge. HCl, after donating a proton, again a proton is an H+. After donating a proton, only the chlorine is left. The H is gone. H is gone with a plus charge. Therefore, the leftover is negatively charged. As you can see, a proton is transferred from HCl to water. HCl is a Brønsted-Lowry acid. Water is a Brønsted-Lowry base. It is a proton acceptor. Well, I don't know how many of you remember what we talked about last time. Last time when we were talking about Arrhenius acid and the base, we kind of used the example of HCl. We said that when HCl is dissolved in water, you're going to produce proton, hydrogen ion, and chloride ion. Now, as you can see, these are 2 different ways to describe what happens when you dissolve HCl in water. Now, which one is correct? Well, as a matter of fact, this was proved to be a mistake. A hydrogen ion, a proton, never exists as a proton by itself in water. A proton in water always combines with a water molecule to stay as hydronium ion. So it is a hydronium ion. This is a hydronium ion. Well, writing it as a proton is a lot easier, simpler, so people accept that. Although we all know now, when protons dissolve in water, they do not stay as individual protons, they always stay as hydronium ions. However, people use them interchangeably. Okay, when you write H+, everyone knows that it is actually a 3O+. All right, so it is not a mistake, it is accepted. All right, look at this again. So if we know that, we know that HCl is donating a proton, H2O is accepting a proton. Well, another fact we want to clarify, I assume we may know it already, but I want to emphasize it again. In the process, if there is a donor, if there's something is donating a proton, there must be something else that is accepting a proton. Does that make sense to you? As a result, a Brønsted-Lowry acid and a Brønsted-Lowry base always coexist. If there is a Brønsted-Lowry acid, there must be a Brønsted-Lowry base in the system. This is one aspect that is different from the Arrhenius acid and base. An Arrhenius acid is defined as an acid. It has nothing to do whether you have a base or not. An Arrhenius base is a base. It has nothing to do whether you have Arrhenius acid or not. But in the Brønsted-Lowry theory, acid-base always coexist. If there is an acid, there must be a base. For many Brønsted-Lowry acids, the proton transfer process in water is actually reversible. So let's look at this example. A carbonic acid dissolved in water, a proton is transferred from carbonic acid. A proton is transferred from carbonic acid to water. Water accepted a proton, becomes hydronium ion. Carbonic acid loses a proton. Now only one hydrogen left. There was two before, only one left. And before it was a neutral. After losing a positive ion, it carries a negative charge now. Well, by definition, carbonic acid is a proton donor, is an acid. Water accepts proton, is a base. All right. Now, as what it is talking about here, it is saying that the process is reversible. So let's look at the reverse process to go from these two back to the original two substances. What has to happen? Can you see that in order to go from right to the left, a proton must be transferred from hydronium ion to the bicarbonate ion? Of course, if water gets a proton, becomes hydronium ion, to go back, hydronium ion has to donate a proton. So to go back, hydronium ion will have to donate a proton to the bicarbonate. All right? By definition, hydronium ion is an acid, Brønsted-Lowry acid, because it is a proton donor. Bicarbonate ion is a base because it is a proton acceptor. Let me rewrite them here again. This is actually a base. This is an acid. Are you guys following me? All right, what we see here is that an acid, after donating a proton, becomes a base. A base, after accepting a proton, becomes an acid. The pair obtained by an acid and the species obtained after donating a proton, or a base and the species after accepting a proton, is called conjugate acid and base pair. An acid after donating a proton becomes a base after accepting a proton becomes an acid. We discussed this. The pair of an acid and a base obtained after the acid donated a proton is called a conjugate acid-base pair. So this is a conjugate acid-base pair. This is another conjugate acid and base pair. We know that a conjugate acid and base pair differ, the two species in the pair differ by one proton. Base accepting a proton becomes its conjugate acid. Acid donating a proton becomes its conjugate base. The acid and the base in the conjugate acid-base pair always differ by one proton. Okay, let's look at in a generic way. HA represents an acid, whatever acid it is an acid. Dissolved in water, donates a proton to water. Water, the base becomes its conjugate acid. Acid, after donating a proton, becomes its conjugate base. So the acid and its conjugate base, they differ by one proton. Water, in this case, water, a base, and its conjugate acid, again, they differ by one proton. An acid, a conjugate acid and base pair always differ by one proton. It is the acid in the pair that has one more proton than its conjugate base. So how do we identify the acid base from the conjugate acid base pair? How do we know which one is acid, which one is base? Again, we just summarized it already. The acid in the pair always has one more proton than its conjugate base. One more proton means has one more hydrogen in its formula and one more positive charge, or one less negative charge in the formula. So let's practice. Try to find out the conjugate acid and the base for some given species. Find the conjugate base of this. Conjugate base will have one less proton. One less proton means proton is gone, only Cl left. Before it was neutral, HCl was neutral. H is gone, it's gone with a plus charge, so the leftover will carry a negative charge. Chloride will be the conjugate base of the acid HCl. H3PO4 conjugate base, H3PO4 is neutral. We know its conjugate base will carry one negative charge. And you will remove an H from the formula. So H2PO4 negative. Everything else stays the same. The difference between the two is one proton. One proton is one H and one charge. The acid will have one more positive charge or one less negative charge. Next one, H2PO4 negative. Okay, the acid itself carries a negative charge. If you remove a positive charge from something negative, the leftover will carry two negative charge. So we know the conjugate base will have a two negative charge. Again, you're going to remove an H from its formula. So it's going to be HPO4 2 negative. That will be the conjugate base of H2PO4 negative. Make sense to you? The conjugate base of the acid always has one less proton and one less positive charge or one more negative charge. There are different ways to say it. All right. Find the conjugate acid of this one, nitrate, NO3 proton. To find the conjugate acid of something, you add a proton to it. A proton means an H and one more positive charge. Right now, the base carries a negative charge. After adding a positive charge, it's going to be neutral. So the conjugate acid will be neutral. Now we need to add H to it. HNO3. That will be the conjugate acid. You add H in the formula and one more positive or one less negative. In this case, is one less negative. All right, find the conjugate acid of this one. Again, you add a proton to it. A proton means an H and a plus charge. Right now it is neutral, so the conjugate acid will be one positive. Add a H to it. Right now it's NH3. Add a H will be NH4 with a positive charge. That's the conjugate acid of it. All right, H2PO4 negative. You know, add a H plus to it, the final species will be neutral. Add a H to it, H2 becomes H3, H3PO4. That's it. Are you guys following me? Wait a minute. Let's look at this one. Oh, H2PO4 negative. In the first practice, we realized that it has a conjugate base. In the second practice, we see that it has a conjugate acid. So a chemical species can have both a conjugate acid and a conjugate base. While these first two pairs is a conjugate acid base pair, that is the acid, that's its conjugate base. The second two species is a pair. This is the base, this is its conjugate acid. So this species has both a conjugate acid and a conjugate base pair. Well, that happens. We're going to talk about that on the next slide. So let's finish this practice now. Are the following conjugate acid base pairs? So we have 1, 2, 3, 4 pairs. They're asking you, are these pairs conjugate acid and base? Check them. If they differ by one H in its formula and by one charge, the one with one more H should have one more positive charge. If that's the case, it is a conjugate acid base pair. So let's look at the two. Okay, this one has one, clearly it has one more hydrogen. Good. Does it has one more positive charge? On the right, it is negative. Add a plus, neutral, that is neutral. All right, this is a conjugate acid base pair. That is the acid, that is the base. Conjugate acid base pair. These two, well, H4, H3, they do differ by an H. Good so far. The one had one more hydrogen, has one more positive charge. Good. That is an acid base pair. That is a conjugate acid base pair. These two, well, of course, no, neither of them has a hydrogen. They don't have a proton in it at all. It is not. This one, oh, the first one does have one more hydrogen in it. However, it has one oxygen here, not have two oxygen here. No. The conjugate acid base pair can only differ by one proton, nothing else. So you don't need to figure out the charges whatsoever. This is a no. It is not a conjugate acid base pair. So far, so good. Now we introduce the amphiprotic substance. It is a substance that can either lose or accept a proton. Therefore, it can function either as an acid or a base. Wow, exactly the case we saw earlier when we were talking about H2PO4 negative. That one can either accept a proton or donate a proton, so it has a conjugate acid and it has a conjugate base. Another example, water. See this pair, this is a conjugate acid base pair because water accepting a proton will become hydronium ion. So this is a conjugate base acid base pair. That's the acid, that's its conjugate base. That's an acid, that's its conjugate base. Makes sense to you? Or you can call this one, or you can call water as a base, and this one will be its conjugate acid. Okay, either way you call it, they are conjugate acid base pair. Okay, you don't have to call the acid and the base is the conjugate base. You don't have to call it that way. If one thing is acid, the other one is conjugate base. If you can call that one a base, you can call this one is conjugate acid. So it's conjugate acid base pair. In the second case, water lost the proton. Water lost the proton. If you take a proton away from water, take one H away, OH is left, and take a positive charge away, a negative charge is left. So this is another conjugate acid-base pair. In this pair, water is the acid because it is donating a proton. And this is conjugate base. Make sense? Okay. Hydronium ion is the conjugate acid of water. Hydroxide ion is the conjugate base of water. These two is a conjugate acid-base pair. These two is a conjugate acid-base pair. However, these two, hydronium ion and hydroxide ion, they are not conjugate acid-base pair. Please be clear about that. They differ by 2 protons. Okay, they differ by 2 protons. All right, let's move on. Find the conjugate acid and the conjugate base of each of the following amphiprotic species, or they will give us some amphiprotic species like water, and then the access to find its conjugate acid and its conjugate base. All right, we're going to do one together. You can do the rest by yourself. To find the conjugate acid of it, you add a proton to it. NH3 add a proton, you add 1 more H, it becomes 4. A proton is positively charged, add a positive charge to it. That's the conjugate acid of ammonia. Conjugate base, let's find its conjugate base. You take, this is the conjugate acid of it. Let's find the conjugate base of it. You take a proton away from it. You remove a proton away. Now there's 2 hydrogen left. You remove a positive charge from something that is neutral. Now it is going to be negatively charged. This is the conjugate base of that. The second one, actually we did it on the last slide. Try to do it here again by yourself. You can verify your answer by going back to the last slide. Well, please try this one by yourself. I'm sure you can do it. All right, that's it for today.